NASA's Voyager 1 spacecraft has just returned a message to Earth that leaves experts speechless. What lies beyond the vastness of space? Join us as we delve into this mind-boggling revelation. Voyager 1 was launched on September 5, 1977, and has spent almost 44 years in space. It arrived at the heliopause, the outermost point of our solar system, in 1990. One of Voyager 1's most notable discoveries was the observation of powerful radio emissions from the region of black holes. These radio emissions were thought to be caused by charged particles propelled to near light speed in the vicinity of a black hole. The observations made by Voyager 1 verified the existence of black holes and helped us understand how they interact with matter surrounding them. The scientific community was stunned when Voyager 1 made a revolutionary finding. It observed a dramatic fall in the quantity of particles originating from the Sun, as well as an increase in the number of high-energy particles originating from outside our solar system. This indicated that Voyager 1 had crossed into interstellar space. But that isn't all. Voyager 1 also uncovered signs of a black hole, which is even more astounding. It detected a beam of particles traveling at nearly the speed of light. This particle beam was created by a shockwave that happened when Voyager 1 left our solar system and reached interstellar space. This shockwave indicated the presence of a black hole. When a black hole forms, it generates a powerful shockwave that expels the surrounding gas and particles. This shockwave accelerates particles to tremendous speeds, which spacecraft like Voyager 1 can observe. But how could Voyager 1 detect this particle beam? Voyager 1 was outfitted with scientific equipment known as the Low Energy Charged Particle, which is the LECP. This equipment was created to detect and measure charged particles in space such as protons, electrons, and ions. The LECP instrument recorded a dramatic rise in the quantity of high-energy particles as Voyager 1 exceeded the border of our solar system and entered interstellar space. The shockwave produced by the black hole was accelerating these particles to nearly the speed of light. But why was this particle stream proof of a black hole? When a black hole forms, it generates a powerful shockwave that expels the surrounding gas and particles. This shockwave accelerates particles to tremendous speeds, which spacecraft like Voyager 1 can observe. Voyager 1's finding of a black hole is noteworthy because it demonstrates that our solar system is not alone in the universe. Other star systems have fallen into black holes, and we can detect their presence even if we cannot see them directly. However, the finding of a black hole presents some interesting questions. For instance, how many black holes exist in the universe? How do they affect the galaxies in which they exist? And most crucially, will we ever be able to harness the energy of a black hole? Unfortunately, we do not yet have all of the answers. However, the discovery of a black hole by Voyager 1 is an important step towards understanding the cosmos we live in. Simultaneously, Stephen Hawking was making groundbreaking discoveries about black holes. In 1974, he postulated that black holes, due to quantum processes near their event horizon, could produce radiation, now known as Hawking radiation. This revelation called into question our understanding of black holes and their behavior, implying that they could progressively vanish over time. Hawking's work on black holes also influenced the creation of string theory, which aims to reconcile general relativity with quantum mechanics. Voyager 1 and Stephen Hawking's discoveries have had a tremendous impact on our knowledge of black holes and the universe as a whole. They have questioned our preconceptions, leading to fresh discoveries and ideas. We now understand that black holes are more than just strange phenomena that devour everything in their path. They also release radiation and interact with the matter surrounding them. The observations of Voyager 1 and Hawking's work have also aided in the development of new ideas and models to explain the behavior of black holes and the universe. David Finkelstein in 1958 published a theory that first, a black hole is defined as a region of space from which nothing can escape. These black holes can then expand by devouring and combining with other stars and merging with other black holes in their surroundings. Most galaxies are assumed to have one in their midst. The presence of a black hole in their centers can be discovered by observing its interactions with other substances and electromagnetic radiation. For example, Mata's visible light, when it falls into a hole in the ground, it is capable of forming an external, although Voyager 1 has yet to detect anything, according to physicists, any indications of such minute black holes. However, they claim that the idea should be considered, and not be ruled out because Voyager 1 is still in operation. Since Voyager 1 is currently sending data back and will continue to do so, this will continue until the year 2030. Additionally, quantum mechanics suggests that empty place isn't really empty, but is instead filled with a roiling sea of virtual particles and antiparticles which pop in and out of existence. This phenomenon is known as vacuum fluctuations, and it occurs as a result of quantum physics' uncertainty principle. How does black hole form? Here's the answer to that. When a big star collapses in on itself, black holes arise. The gravitational force becomes so powerful that nothing can escape it, not even light. The event horizon is defined as the point beyond which escape is impossible. When an object passes the event horizon, it becomes trapped in the black hole's gravitational attraction. The stronger the gravitational force becomes as the item approaches the center, or singularity. When items fall into a black hole, they begin to spin around it, forming an accretion disk of gas and dust. This disk's friction warms the material, causing it to emit light and other forms of radiation. Contrary to popular assumption, black holes do not exist in perpetuity. Hawking radiation, hypothesized by Stephen Hawking, proposes that black holes steadily lose mass over time as they emit radiation. The black hole will eventually disintegrate. Black holes can potentially merge, resulting in even larger black holes. When this happens, the ensuing black hole generates a burst of gravitational waves, which advanced equipment like LIGO can detect. Despite their enigmatic nature, black holes play an important role in shaping the cosmos we inhabit. They function like cosmic vacuum cleaners, sucking in and consuming anything comes too close. They are also important in the development of galaxies because their gravity influences the movement of neighboring stars and gas. Black holes remain one of the universe's most perplexing things, yet our understanding of them is continually developing. We may one day be able to unveil the mysteries of these extraordinary objects and obtain a better understanding of the universe we live in, thanks to new technologies and scientific advances. One particle could fall into a black hole. As the other escapes through the black hole in what is now known as Hawking radiation, the quantity of radiation released grows in proportion to the black hole gradually losing mass due to the evaporation process. He proposed the Hawking radiation theory, which states that black holes generate radiation and lose mass over time. This is induced by quantum mechanical phenomena near the event horizon, which might result in particle-antiparticle pairs. Did you know the temperature is higher for smaller black holes weighing about at tens of billions of tons should be really hot? This is because a black hole's temperature is inversely proportional to its mass. A black hole's temperature drops as its mass increases. This indicates that larger black holes emit less radiation than smaller black holes, which emit more radiation due to their greater temperatures. Black holes, according to Hawking, are not completely black. They produce a little amount of radiation due to quantum mechanical phenomena around the event horizon. This radiation causes black holes to lose mass over time, eventually causing them to evaporate completely. Hawking also postulated that black holes have temperatures and entropies that are proportional to the amount of information they contain. This concept of black hole entropy has been an important area of study in quantum gravity, leading to the invention of the holographic principle, which claims that the information stored within a black hole is encoded on its boundary. Kip Thorne is an astrophysicist who has dedicated his career to the study of black holes. He proposed the concept of a wormhole, which is a hypothetical tunnel that connects two places in spacetime. Thorne's work has influenced science fiction, and the concept of a wormhole is frequently exploited as a story element in films and television series. Haven't black holes in Voyager 1? Discovery blown our minds, right? Then hit the subscribe button to get updated on more such videos. Andrea Ghez is another astrophysicist who has made groundbreaking findings in the field of black holes. She and her colleagues discovered a supermassive black hole at the heart of our galaxy, the Milky Way. This discovery has given us important insights into black hole behavior and the consequences they have on neighboring stars and gas. Did you know? Voyager 1 just made contact with a highly advanced object in space. Check that out as well. We'll see you in the next video.